My name is Ryan Fordner, and this is my Physics 2212 Lab 4 about circuits. First, I will go over the purpose and key concepts of the lab, then the design and the experiment itself, then I will go over my graphical analysis, and finally answer the two what-if conclusion questions. The purpose of this lab is to use the principles of energy conservation and current conservation to predict circuit behaviors, measure the actual value of conventional current and the potential differences, and examine the behavior of the ohmic resistors and capacitors. I use the online circuit builder to complete this lab, so any errors could be due to the program itself. Finally, a preview of my results. I found the RC value to be approximately 6 seconds. Here are the definitions of a circuit, capacitor, and potential difference for this lab. Please pause to read. The conservation of charge says that the total charge of a system is constant. Then there are Kirchhoff's circuit laws. The current rule says that the sum of all currents in a system at a point equals 0. And the loop rule says that the sum of all potential differences around a closed loop equals 0. Ohm's law helps us find the current in the circuit. And finally, circuit steady state says that there's no change in overall voltage over a long period of time. The system in this experiment is the circuit, and then the surroundings is Earth and everything else in the digital model. We're going to assume that the resistance of the wires and the ammeters is negligible, and the electromotive force, or EMF, equals the delta V of the capacitors plus the delta V of the resistors. There are multiple parts to this experiment. Part 1 is I consider multiple circuits consisting of 2 batteries, 2 resistors, and ammeters with voltmeters. And I need to predict the currents I1 and I2. And then part 2 says to investigate an RC circuit to observe how capacitor charges change. So here is my circuit for part 1 with the two 1.5 volt batteries, a 47 ohm resistor and a 100 ohm resistor with the 2 ammeters. So according to conservation of charge, I1 must equal I2. So both ammeters read at 0.02 amps, which lines up, like I said, with Kirchhoff's laws and Ohm's law. If connected backwards, then the signs would change, so the ammeters would read negative 0.02. And once I put the voltmeter where the ammeter is and open the circuit, the current reads 0 because the circuit is no longer closed and no current can flow. Here's the second circuit I created. So I closed the circuit again and measured the voltage at different spots along the circuit, all listed here. And the total voltage equals 0 after all my measurements and adding them all together, which aligns with the conservation of charge and Kirchhoff's laws. There would be no change in current, 0.02 amps, because the voltmeter has a high resistance and doesn't carry any current. Using this data, I approximated a potential difference graph here. The thinner red lines are my data. Here's my model of the third circuit system. Here I place an ammeter parallel to the 100 ohm resistor, and the current reads a little bit higher at 0.06 amps due to splitting the node, and the ammeter has 0 resistance, so the overall resistance of the circuit decreases, so the current actually increases. So then I calculated the resistance of the 47 ohm resistor and the 100 ohm resistor using this I equals VR equation. And for R47, it is 34 ohms, and for R100, it is 16 ohms. And of course, the ammeter and the wire we assumed earlier to be 0 ohms. Here are the descriptions for the circuits set up in part 2. And the purpose of part 2 was to analyze how the capacitor charges change over time. So when the light bulb was at 10 ohms, the charging time was about 10.3 seconds and the discharging time was about 12.1 seconds. When it was 20 ohms, the charging time for the capacitor was 18 seconds and the discharging time was about 22.8 seconds. Using the time data, I calculated the ln delta V over delta V initial in these columns here, and using the equation given in the lab instructions, I found the negative TRC to be 0.1519. And using any point on the plot from there, I could find the RC value to be approximately 6.3 seconds. And the expected prediction using just RC equals resistance time capacitance equals about 6 seconds. So my prediction was very similar. To conclude, I'm going to answer these two what-if questions. Firstly, if I had used an actual ammeter instead of an ideal ammeter, there would have been resistance, so the current would have been lower in real life for each part of the lab. Secondly, if I was using a real battery to charge the capacitor with no resistor, then the capacitor would reach full charge at nearly instantaneously, so if no resistors were present. The resistors slow down the current and flow of charge. Thank you for watching my presentation.